Hi everyone. So today we're going to quickly go over titration curves. I want to quickly go over some key points about titrations, and then it will just be like trivial stuff, and then we'll go into titration curves and pH curves and what you need to know. So you need to know about volumetric analysis. That's like the whole point of titrations. We want to use a standard solution, which is our known concentration, and we use it to determine known solutions, which you guys know. Common apparatus that you need to be aware of. So it's obviously the volumetric pipette, burette pipette, and graduated pipettes. So the whole thing that I've brought that up is that because they like to use them in terms of uncertainty calculations. So remember how we talked about how to work out uncertainty. You basically they'll give you the uncertainty for each, maybe a pipette. They'll say, can you work it out for one of the titers? You look for how many times in the method they used it, times it, whatever, and then you should get your value. Then we're going to talk about equivalence points. So this is all the nitty gritty that is quite easy to understand. And I've got some harder questions but we'll cover all bases. So an equivalence point occurs when two solutions have reacted completely, so we can use an indicator to show this. So we know, for example, in a titration, that little point that we can indicate for pH is when it actually has finished. The titration has finished. It goes that nice light pink color, and then we can basically say that's our equivalence point, and we use a pH to indicator to determine the pH of what it actually is. We can actually plot the pH curve using these values that we generate. So this is an example of a pH curve. So you've got a pH on this side, you've got volume. I'll get into specifics about the volume soon. The whole idea is that you have a strong acid or weak base or whatever, and you generate something called an equivalence point. Now, the equivalence point is the point where it's in the middle or it aligns in this vertical sort of section. Now, the most important parts are obviously this equivalence point, but we typically in calculations like to rely on something called the equivalence volume. So that is where obviously you'll find the point where it's vertical, read down, and that is your volume. So I haven't been so specific. I'll probably read, it should be straighter, but like I've got a drawing, I haven't got the best drawing skills. And then obviously you can read off the pH of the equivalence point. So what do you actually need to know? You need to know how to basically be aware of the sort of graphs that you need to know. Now, these two look really similar, but I'll talk about how to obviously identify. If you look at your starting pH, that mimics your acid. Now, if you look at my axes, these are all volume of base being added. That's the one that is the main thing. So you look at your starting pH, and then that is your acid, and then the end pH or your final pH resembles your base. So you can see that they're the highest points, and that's why we know it's strong, and then the strong base. If it's a strong acid and a weak base, your ending point, this should be a bit lower. Hence, if this is a bit lower, then your vertical point should slowly get smaller, and smaller, because there's less of a range between them. You've got a weak acid and then strong base. We're high at 14 here, so we know it's a strong base, and we know it's a weak acid because it's starting earlier. And then eventually you get a weak acid and then a weak base, so your ranges are way smaller. And then also you've got the starting pH as higher to show it's a weak acid, and then therefore those are the sort of things that you need to be aware of. Now, I wouldn't go up straight away and just learn them. What I would do is obviously just know about the starting and then end points, and then you should be fine. So there's no need to just memorize it. You should be able to kind of predict what it would look like. There's another thing. So remember when I said to you it's a volume of base being added at the bottom? They can change it to say volume of acid. Now, the only thing that is different about that is with the volume of acid, it is a mirror image of what these would be. So you start off with your like a mirror image of what the typical curves would be like. I've never really seen this happen, but they could ask you it, so just be aware. So then that leads us on to indicators. So acid plus base indicators are basically weak acids that dissociate to give another color. So if you think about it, it's kind of like equilibrium, where if you'll shift to one side where it's with the acid, and then shift to the other side where it's a conjugate. That's why we like to use weak acid, because we know it's got acidic properties and then in conjugate acid properties. You need to also know that the pKa of an indicator is the same as its pH in the endpoint. We'll refer back to this a bit later, but typically pKa and pH can be similar in different points. So typical indicators that you need to know for the different circumstances are strong acid and strong base. They like to use methyl red and phenolphthalein. Strong acid and strong base and weak acid, phenolphthalein. Strong acid and weak base, you've got methyl red, and then weak acid plus base. There's no suitable indicator, right? Because it's all determined on your endpoint and your ranges. So if we look back up our picture, you've got like an undetermined sort of endpoint going on, and the equivalence is so small in range values. So that's why we don't really have a pH that is suitable enough for the both of them. So when you are picking an indicator, now they like to ask this question, if they ask you to pick an indicator, look at the one that corresponds the best to its equivalence points in your ranges. So if you have like a weak acid and a strong base, which sort of ranges does the curve sort of fulfill, and match that to the ranges that they give you the P indicator, and give the most best educated guess. Then they could ask you to compare curves. So I've seen a question where they said, oh, originally I reacted a weak acid and a strong base, but now I've decided to do one where it's a strong acid and a strong base. So what would be the difference in curves, for example? So that obviously you need to look at your endpoints. Are the endpoints the same? Compare your final pH, compare your starting pH. So if you started with a weak acid, your starting pH is going to be a lot more higher than it would be with a strong acid. You need to also look at your vertical section. So remember, the weaker you go, the smaller your range. So that's how you sort of compare. So those are the sort of parameters you need to be looking at and comparing them. In terms of maths, now I've seen two questions. With OCR in the 2024 paper 1, they asked if you can draw a line of best fit and then calculate the concentration. So obviously I've drawn that in, but just obviously fill it in, draw the line of best fit. Now it says to calculate the concentration of ethanoic acid. So you've got a volumes, you've got one volume and one concentration and a equation. Now with equations, remember how I taught you guys, it's basically like a little clue to show you that you're going to have to do ratios in the question. So if we look at my axes, I've got the volume of the base, right? So I know if I've got a volume of a base and I know its concentration, I could probably get the moles. So I'm going to read down from the equivalence point, and I'm getting 12.5. That's my equivalence volume, to which I can use a concentration given to me in the question and then get the volume to give me the moles. Now, this is my little indicator to say that we don't actually want barium hydroxide, we want ethanoic acid. So we look at the 2-to-1 ratio in the equation, and I know if it's 2-to-1, I can just times that molar value by 2 to get the moles of CH3COOH. To which, if I've got the moles, and in the question they've given me the 10 centimeters cubed for the volume, I can times them to get the concentration. So that is how to do that in a nutshell. Then AQA has a slightly harder one. So it's asking them to find the Ka of propanoic acid, and this is the AQA paper 1 2019. So you need to know that I've wrote some parameters, but it's a weak acid, because obviously it starts higher, and a strong base. You've got Ka. You need to know that Ka is half the neutralization point, and at the half the neutralization point, pH and pKa are the same. So that's a good point to take note of. So what I would do is I would need to work out my equivalence point, because that's my neutralization point. So if I work out my neutralization volume, I get 19.5. Now, with the prophecy that whatever I gave, it's half the neutralization of that. So that's why I'm going to do 19.5 divided by 2 to adhere to the rule that I gave you. Then, because it's 19.5 divided by 2, you get 9.75, to which you read off from 9.75 to get the pH. We're getting 4.85, and then we can fulfill this rule where the pH is equal to the pKa. If I know my pH is 4.85, I know that's equal to my pKa, to which I can do 10 to the power minus 4.85 to get my Ka. And that is probably the hardest questions. Other than that, it's a lot of the time we're interpreting values and picking indicators. So that is pretty much it in a nutshell.